Hi, welcome to Track B AI and ML Foundations. Today is part 2. We are going to look at how classical AI is reborn in 2026. Every agent that we are building or using today typically does search, planning, and some form of knowledge representation. And these are not new concepts, these were existing earlier as well. They are just reborn in a new shape, and that's what we are going to look at today. At the end of the class or this short session, you'll be able to frame a workflow as a state space. When I say state space, we are going to look at what are states, what are actions, what is a goal test, and what all these raw materials that every agent needs these days. We will also be able to explain why search explodes. uh, Options multiply exponentially. We will see why does that happen, and why agent and reasoning runs need step and tool budgets. We will also read an agent as strips with a neural planner. That's what we will be able to explain as tools are actions, context is the state, and classic failures are old planning failures. We will also understand how to choose rules versus model by failure mode. Symbolic systems fail loudly and predictably, while LLMs fail silently and confidently. And that that's what we are going to learn through this journey. We're going to start with search. We'll understand what state spaces are, how breadth first and depth first search happens. We'll understand what are heuristics, and how is A star versus minimax compared to BFS or DFX in DFS in terms of search. We are going to look at planning. Planning is nothing but new to 2026. It was used earlier as well in strips in 1970s. We're going to look at what are preconditions and effects, and how does the agent loop work. We will also look at knowledge representations. We look at logic and expert systems. Why did they fail? Because of certain bottlenecks, and how knowledge graphs came into existence. We will also bridge this gap between the symbolic AI that existed earlier, and why did, though I would not call it died, but it came into an alignment with neural systems. And today, a combination of these two, that is neurosymbolic AI systems, gives you a much more competitive advantage compared to just either symbolic or neural systems. And one idea that you I want you to take away from this session is, if you give a machine a space of possibilities and a way to move through it, and tell it when will it win, it will fall out of disciplined search. And that's the whole context of this session today. In the first part of this session, we're going to look at search, and we are going to look at what do we mean by search, and when we give a machine a space of possibilities, uh, how would it explore that space. So imagine there is a state, and a state is like a snapshot of the world, and everything that a system is trying to do is navigate through that state. Okay. um, an example could be categorized ticket. It has a definite state. It has been done. It's in a particular state. For an email, it could be no reply yet. It's a state. The actions are the moves that you can make from a particular state. And typically in the support agent example, it could be like, hey, retrieve a ticket, draft a response, escalate to a particular human, ask for more details. All these are actions that a agent can make from a particular state. Transitioning, what does each action change? Yeah. Draft, when a candidate replies, and it exists now, that's a transition from the draft state to a ready state. A goal test, how do you know you are done? How would you know that, or how would the support agent know that its task is completed? Either the customer has confirmed or the ticket has been resolved. That's how the support agent gets to know that it has succeeded. Yeah. So what we're trying to say is, once a problem has been defined, we need is a state, an action, and a goal test. Yeah. And general algorithms can solve it with ease. And this is the precise reason an agent framework is asking you to define it. Yeah. And there are two ways to explore this blindly. If you even have to close your eyes and navigate that state space, it's easier to navigate in these two models. One is breadth first and the other is depth first. In breadth first, you explore all the nearby options first, or you take all the actions that are near to you, and then you move outward like a ripple. When you drop a stone in a stable water or lake or a pond, you'll see the ripples forming outwards. Yeah. So the first ripple is always closest to the stone. Breadth first works similar. Yeah. Depth first is the other way around, where you have multiple paths and you take or dive deep into one path, and if you find the destination, you reach there, or you come back, you backtrack yourself to the origin and then start on the different track. So BFS is guaranteeing the shortest path, whereas DFS is pretty cheap on memory. Why is breadth first guarantees the shortest path? Because you're always taking the closest uh, elements to it and then going wide, wide, wide. So it helps you find the shortest path fastest. Whereas DFS is cheap on memory, because at any given point in time you only have one route to be kept in mind, or one path to be kept in memory. BFS holds a whole frontier. That is, it captures in memory all the uh, closest nodes, and then the next closest nodes, and then the next closest nodes, and so on until it finds a destination. That's why it's heavy on memory, whereas this is cheap on memory. DFS can wander forever and miss the shortest path. So in the goal of finding the end result, or in that journey, sometimes DFS forgets what it is trying to do, and it might miss the shortest path, but ultimately it will get the result done, or get the um, success criteria. Sometimes brute force is correct, but at the end of the day it's pretty useless. Imagine you have the graph that you want to traverse, and from the root, every branch, you branch out, you have 10 new branches being created. So at depth 1 you only have 10, but at depth 2 you have 100, because each one of these depth 1 nodes is uh, leafing out or branching out to another 10 depth 2 nodes. Similarly, this goes to 10 another, so on. So everything multiplies by a multiple of 10. While brute force says go and search everything, it sounds faster. Yeah. But at the same time, the agent runs cost 10 to 100 times every single cell it is touching. Yeah. Exploration is not free, and it becomes exponential in nature. Yeah. Every time you touch another 10, there is an exponential multiplication factor growing in. Yeah. And that's the villain of the week. Yeah. Every clever method, heuristics, AlphaGo, Monte Carlo, or MCTS, Monte Carlo, tree search, neural value functions, is a way of avoiding looking at most of the tree. You don't want to go through all these elements to find the shortest path. So how do I find which is the right branch to be picked up, so that I reach the goal faster? Yeah. Just let the agent try everything. Is this tree? Yeah, sorry, this should have been in this tree. And that is the brute force method. And brute force method, the computation is heavy, and when the compute is heavy, the bill is also higher. And A good guess will always beat brute force. In brute force, you always explore all the paths. In a good guess, which is like a cheap estimate of how far a state is from the goal, which we call a heuristic. Good guess is nothing but a heuristic. Uh, it will always beat a brute force. Yeah. So imagine A star ranks each option by a function where the function is equal to g of n plus h of n. Yeah, n is the number of nodes, for example. Yeah, the cost already spent plus the estimated cost remaining. So g of n is like the cost of a particular action done. H of n is the estimated cost remaining. So we need to minimize for this. Yeah. So if the guest never overestimates, that is, it doesn't become large, A star finds the best path while opening far fewer options than blind search. Blind search is your BFS and DFS, as in you're navigating until you find the result. Yeah. So how does this work in 2026? Your Google Maps routing, your game pathfinding, your logistics, yeah, everything uses a neural network, yeah, and it's using a learned heuristic there. And what does that heuristic? That's like a star, where we are saying that hey, at one particular point when you reach a particular destination, for example, let's say you want to travel from uh, Delhi to Bombay. You start from Delhi, and after a certain point you reach a crossroad. Google Map will calculate saying that hey, once you have reached here, what is the total number of kilometers covered, and how far are we remaining? Yeah, that's what it is calculating, g of n plus h of n, and all the math that it does to tell you how much time it is remaining, how fast you are going, everything is like a star function. Yeah. So next week we are going to learn something very interesting, and this is the bridge to that. Yeah, AlphaGo's value network is exactly h of n. So AlphaGo, we remember from week one or part one, that helped us win a Go game uh, from DeepMind. AlphaGo was built by DeepMind, which was headed by Demis Hassabis, and in winning that AlphaGo Go game, all they were asking was how good is this position. Yeah, when we say how good is this position, we are saying g of n plus h of n, how minimal is this. Yeah, and that was learned from data instead of hand design. So nobody handcrafted those parameters, those were learned from the data themselves. And we saw that interesting move number 37, which was amazing because no human so far had thought of making that move. And this AlphaGo system or intelligent system made that move, hence showing that given sufficient data, we could find always new patterns. And minimax does a little different. What it does is it plans against an opponent. So we'll look at this in the next screen, how this will go as an example. And that was the wall that was set up by AlphaGo. Deep Blue beat Kasparov at chess in 1997. This way, Go was immune. It had too many moves and no hand writable way to score a position. So when Deep Blue beat Kasparov at chess in 1997, there was a lot of data, but there were hand written moves in chess. On if you arrive at a particular point, what could be the next move? Yeah, in chess it's somewhere around 35 moves that you can make from a given position. From a particular state, you can move any of the coins in 35 unique ways. And in Go, sorry, coming back to chess, it was 35 moves. So you always had the option of saying which one of those 37 moves, 35 moves will I make. Whereas in Go, there are too many combinations. There are 250 and above moves that you can make. So it was hard to handwrite which move can a particular person or system make, uh, given it arrives at a particular point. And that's why it had to learn on its own. We could not or we as humans cannot hand engineer so many elements. Yeah, and that was a cliffhanger. When hand-tuned evaluation and exhaustive search both failed, we learned that the evaluation and steer the that, that the evaluation and steer the search. You learn the evaluation and steer the search. Yeah, so we are saying that we learn the evaluation on our own and we are steering the search. And that's very clearly explained through these three diagrams. Breadth first search, we start at the root, we look at all possible nearest options, so A, B and C, and we visit the nodes, and then we go to the next nearest nodes, and then next nearest nodes, and finally to the end. Yeah, imagine doing all of this. It requires so much memory for us to store this, and it takes a lot of time to do this. So much memory, so much compute. In A star search, what it does is it takes a function f of n is equal to g of n plus h of n. It identifies the next nearest element. Whichever function gives it the lowest score, it navigates in that direction. Again, it checks the f of n function, it finds the lowest score, it goes there. Like this, it keeps going until it finds or reaches the ultimate goal. Yeah, this is A star or heuristic based estimates that it's trying to do. With minimax, which is like a game tree, there is a min and max game being played. So imagine you are player 1 and you are choosing the option of max. You always maximize the score. And then what would you do? You'll play against a player who's always minimizing. In this case, when you are at root S, you check the nearest move, whichever is the highest score. For example, 5, 0 and 7. You'll select the 7 because you are playing for max. When it comes to C, player 2 is playing and he is trying to minimize. So when he goes to the next move, ideally this number should have been closer, 4 and 8. He's checking for the lowest score. Between 4 and 8, 4 is the lowest score. He goes here. And once he has come to 4, which is CH, then he's trying to maximize. You as player 1, you're trying to maximize. Between 4 and 7, you select the 7. Yeah, so ultimately you reach here and the graph found is S, C, H and 7. Yeah, that's the path taken until you reach here, and that's the min-max game being played. Yeah, and that's and that brings us to the next interesting part, which is planning. Planning is nothing but you're trying to achieve a particular goal, and you're trying to do that using certain search conditions or actions. So strips was something that was built in 1971. It was a framework, if I can call so, and that had simple parts on how to describe an action. Okay, so what it said was, if you're trying to plan something, there were three things that needed to happen. One was preconditions. Yeah, what must be true first for that planning or action to happen. Okay, and example, if you wanted to send a reply to that support agent thing that we were trying to do, the draft approval step needs to be true. Your draft has to be approved, only then send of reply will happen. Add effects, the reply would sent would be true. Yeah, what this is what becomes true after the action is done. If there is a change or delete of effect, even what will happen in that case, meaning what stops being true. In this case, we are expecting that the ticket that was open earlier will now not be open anymore and it will be closed, hence ticket opening will be false. Something that was built in 1971 is still being used in 2026. Yeah, we give a planner a start, a goal and action, and we describe those steps, and whatever these agents are doing, all they do is they search for the order of actions that reach the goal. That's all they're trying to do. So if you can strip away all the formality or words, all they do is think, plan, act on that plan that we have put. We observe whether we have achieved the required thing. If not, we create a loop and go back to this plan. Yeah, so what are actions? Actions are nothing but tools that we can do with something that are given some context with preconditions. Yeah, the context window is the state, the objective is the goal. Yeah, we observe for that goal to complete. And the loop, the think, act, observe. Think, act, and observe. This becomes the loop for us. Yeah, or it becomes a sequence. So, the failures, whatever failures we are talking about, are old failures. We haven't designed any new pattern now. Yeah. So, the no goal test loops forever. Yeah, a wrong effect model thinks it succeeded when it didn't. Missing preconditions call a tool with bad inputs. Yeah, if you don't give the right data, the tools that are gonna act on certain tools, the LLM that's gonna act on certain tools is gonna miss a lot of things, and then it'll incorrectly execute some steps, and you will not succeed because you're you're not doing it right. Okay, so when you spec an agent in weeks 10 to you're writing strips operators in prose. Actually, we are doing all this. Yeah, so that is the vocabulary we need to review the design. Yeah, so this is how that strips was there. Strips twin was state, action and observe. Yeah, think, action, observe is what we are doing now. Yeah, think, act and observe. In thinking, what are we doing? We are reasoning about what to do next and decide the next action. In act, we are calling a tool to perform an action in the real world. And in observe, we are observing whether, hey, the result that came out of this action, what needs to be done. Does it go back and update the state, or does it go and test whether the action is complete? So it performs one of these steps. Yeah, if it is change in state, it will go and update the think step, which is the planning step, or the context step, and from there it will flow again. If it feels that if it has completed, we need to validate against the goal that we have set. If it is not met, we go back. Yeah, if it is completed, we mark the loop as done and exit. Yeah, and this is where the strips twin action come into picture. Here it was operator, here it's action, and it's the resulting state that we are trying to observe. Just remember here that while here we have a goal, in strips we did not have a goal. Yeah, without a goal test, the agent keeps in loop forever. This loop will keep playing again and again without moving out to the done state. And that brings us to knowledge representation. One of the most important concept that we will learn this week is knowledge representation. Yeah, this is what the machine knows. Yeah, and how it stores fact it can reason over. LLMs have minimal weights with them, or data with them in a vector representation, but how does it store these facts that it can reason over? That's what we are going to look at, knowledge representation. In the oldest of the old systems, these were simple if then rule conditions. Example, mice in XCon that we saw in week 1. These were the systems that were developed. Yeah, first one was developed to diagnose infections. Given a state or diagnosis, what is the disease that the person has been affected with? That's what mycin was trying to do, and it was very handcrafted rules. There was an expert sitting in the system, and he would write a if-else condition saying that, hey, if this happened, then go to this question. If that question is true, then go to that question, and so on until it arrived at a particular disease. In XCon, it had the ability to configure so many combinations of materials to come up with a system automatically that saved millions of dollars for a particular company when they were trying to build systems for their customers. So XCon approximately saved $25 million, and this is what we are talking about, 1980s. Yeah, it was huge then. Yeah, and for a moment people thought, yeah, AI is nothing but a big pile of rules, and that looked like the feature as well, because people were saying if I can extract that knowledge from humans and create that huge pool of if then rules, then we are done, AI is working. But what happened? It hit the walls, and the three walls that it kept hitting with these if and then rules is acquisition. Firstly, in acquisition, the whole human knowledge had to be extracted out, and that was the challenge. Humans could never hand author all of that knowledge. Yeah, experts couldn't explain what they know. That was the biggest challenge. Brittleness, edge conditions always broke. Yeah. And these rules were kept breaking for various new scenarios and so on. Maintenance was a challenge. Imagine you had to fix one of the rule in that 600 plus uh, rules. Mycin had 600 plus rules created. Xcon had 1000 plus rules created. So imagine you had to change one rule. You wouldn't know how will how it would impact the other rules, where to make that change and why. Yeah. And that's why machine learning won instead of handcrafted rules, because hand authoring knowledge didn't scale. Machine learning was learning it from data. And LLM is the extreme version where we are saying that, hey, you don't have to handcraft even the features. It learns everything from the data. Yeah. And it absorbs these rules from the whole of internet also. And two ways to be wrong was these expert systems or if then rules were always failing loudly, which was good in a way because they were predictable and auditable, whereas LLMs, they were failing silently, which was a con for them because they were fluent and they were confident regardless, and we never know when it went wrong. In expert systems, no matching rule, no answer. If there was not a condition met, we would never know what the answer was. In LLMs, there is always an answer. Yeah. It doesn't mean that it is always right. Sometimes it's wrong as well. In expert systems, the traceability, uh, uh, the awareness of why a certain thing failed is a little more clearer, whereas in LLMs, it's a little blurry in nature. You can't tell whether it erred or not. Okay, so we need strong guardrails, constraints there. And knowledge graphs came to help us in LLMs. Yeah. And how does this work? Here we put everything like facts as a network. So everything is connected to everything, and entities joined by typed relationships. Yeah, dots and labeled networks, not paragraphs. Yeah, so everything became a relationship to uh, each other node, and that's what we are going to look at it. Yeah. And the structure helped here. Why? Because the facts are linked together, and a computer can follow the graphs or arrows to answer those questions. Yeah. Imagine you are asking, is Paris in Europe? Yeah. How would you do? It will hop from Paris to France because Paris is the capital of France. And where is this country? France in Europe. So is Paris in Europe? Yes. That's how it's going to answer. And why it matters now? Because we always seen GraphRag where we are able to walk a knowledge graph, so an LLM can look up verifiable facts instead of guessing. It's not guessing anymore, it knows how to navigate this graph. Yeah. Google's answer box completely works this way. So instead of giving you just the link from where the text exists in a particular website, it's now able to answer because it's able to grasp the relationships between those words, bring it into context, and show us that answer. Yeah. And in 2026, that's a neuro symbolic thing that we are talking about. The LLM brings the fluent language, the graph brings a verifiable structure. Yeah. This is the if then rule condition that we are talking about, the symbolic part, LLM being the neural part. Yeah. The graph keeps the model honest because it's again based on the actual data in the graph. So imagine if you built a graph like aspirin treats headache. So next time somebody asks what solves headache, it's going to look in the reverse and say aspirin is able to treat headache. We just looked at an example where we said, hey, is Paris in Europe? So Paris being capital of France is in Europe. So yes, it's going to answer as yes. Okay. And these are individual nodes, then there are relationships between, and it can do a multi-hop. For example, if you ask, hey, where did croissants originate in, it can tell you France. But can you, if you ask about which continent does croissants come from, it can say, hey, croissants originated in France and France is in Europe, so croissants come from Europe as a continent. We can do that. If somebody asks Louvre Museum, where is it located, we can always say it's located in Paris. Paris is capital of France. France is in Europe, so Louvre Museum is in Europe, or Louvre Museum is in France. We can derive that relationship there. Yeah. That's the multi-hop part. It can hop against multiple stops to find the right answer. Yeah. And why does it matter now? We understood that LLMs are great at language but can be unreliable with precise facts. Yeah. And pairing an LLM with this graph or a knowledge graph lets the model look up verifiable facts in this multi hop step, and it does not guess anymore, it gives us the right answer. And this is the neurosymbolic AI that we are talking about in this step. Yeah. And that brings us to the last step, which is while the neuro while the symbolic AI lost a representation war, it couldn't represent the data in if then conditions, but it won the control structure war. When we say control structure war, we are saying that hey, if we had to be very strict about getting the answer out, the facts right, then at some point in time we need to look at symbolic AI. Yeah. The symbolic idea that we are taking from 1950s to 80s is state space search that was created. Here we are talking about agent action spaces and reasoning model search. Yeah. Here it used a star heuristic h of n to optimize the value. Here we are talking about neural value and policy networks that AlphaGo invented, or we descended from these frameworks. We looked at minimax and alpha beta. Alpha beta is nothing but a minimax version of uh, one person taking the alpha route, one person taking the beta route. Yeah. And Monte Carlo research that we are talking about in games and reasoning come come from minimax. Yeah, we looked at strips planning. We are talking about the react loops in agents that system uses, reasoning and acting loops that we are talking about. That comes from strips planning. Knowledge graphs and logic, that was a part of symbolic ideas where data was being stored as if then else conditions. Today it's being pushed to graph rag. We are using schemas on top of that to pull the data together and keep the answers in structured grounding. Yeah. Symbolic AI is has not lost the game, and it is back for the very reason that it is being used for control structures, and that's what neural agents need today. Because if it is only text based, weights based, they tend to hallucinate, and we don't want to go there. And that's why neurosymbolic is the best combination that we are seeing now. Neural for perception, language, and learned intuition, this is what we are using it for. And symbolic for planning, verifiable facts, and auditable logic. So what does it look like when we want to build a real strategy? Yeah. So we are going to use pure LLMs which are unreliable on multi-hop facts and long horizon planning. We will not use LLMs there, and that's exactly where symbolic systems are good at. So the combination is often more defensible than either alone. Yeah, we don't have to use them separately or one or the other alone. We can do a combination of them. And a poster child example is of DeepMind's alpha geometry. Yeah, a large language model that proposed proof steps. Yeah, a symbolic engine that verifies them. Yeah. The one thing that I would recommend us to do is, hey, ground the LLM with a knowledge graph, or give the agent a real planner, is often what turns a flashy demo into a trustworthy product. Instead of just saying hallucinate based on the weights that the model has been trained on, if it is based on a knowledge graph, it will give much more trustworthy answers, and it will become a trustworthy product. So neural is on the left, where we are saying hey, it's purely trained based on perception. It turns raw pixels, audio sensors into meaning. Yeah. And here it's more about your planning, the sequencing of actions to achieve certain goals, and so on. In neural you're talking about the language, how it understands and generates natural language. Here it's more about verifiable facts, because that's what symbolic systems were built to solve for. They wanted answers coming out in deterministic nature. Here it's about learned intuition, where we are saying that hey, it captures the patterns and probabilities from large amounts of data. Here it is about handcrafted rules and logic that are exact, explainable, and machine checkable. We cannot uh, be probabilistic here for certain compliance, for standards, and so on. And that's where symbolic nature becomes very symbolic AI becomes very important. So strengths are, hey, this is great at perception, language, pattern recognition, and generalization. This is good at exact, reliable, explainable, auditable, and goal directed tasks that we want to achieve. Here we are looking at some good weaknesses when I say neural, because it's unreliable at precise facts, because facts keep changing, it's hard to train models, and so on, hundreds of reasons. Long step by step reasoning and guarantees of correctness is low. Whereas here it struggles with perception. There is no natural language, and handwritten knowledge is pretty hard to scale, maintain. It's brittle. Acquisition of knowledge is very hard. We just looked at all the reasons. And alpha geometry or by DeepMind just gave us that as an example. In a neural model that proposes the next proof steps, it collected that knowledge, it passes it to a symbolic engine that checks the logic and validity, and out comes the result that are verified in nature. Yeah. And if you had to look at some example use cases, I would say LLM plus knowledge graph. If you had to give a precise answer as a support agent, an LLM will not have the context, it will not have the facts, because it's not trained on the data. But if it is associated with a knowledge graph, the answers come grounded in verifiable facts. Agents, if you had to build, it needs an LLM plus a planner. If you had to plan for long horizon tasks with checks, then you would need LLM plus planner. If you need vision model plus rules to detect objects and apply basic business rules, then you would need a combination of both. Yeah. So that's where neurosymbolic system comes into play, and we are saying that they are complementary in nature. It makes the whole system constrained and grounded. The results are verifiable and safe, and it's a collaborative nature. Neural proposes, symbolic verifies, plans, and refines. So there is a super deadly combination between these two, that's building reliable agents, yeah, that are capable, trustworthy, and explainable at the same time. Here are some misconceptions that are traps that we should avoid. Symbolic AI is dead history. No, it is not. They became the control structures that are running inside every agent today, and the its older style of representation has lost the touch, but everything remains the same. You know, an LLM agent invented planning. No, it did not. Planning is Strips 1971. We only picked you know only who picks the action changed. Yeah, so LLM is picking the action here. Only that part has changed. The planning is still the same. Yeah. More search is always better. Not truly. Search is exponential. We looked with an example. If every search had to search again 10 times, so it grows exponentially. And the optimistic or most optimal thing to do is look at less of the tree. Yeah, look or navigate less. uh, One trap to avoid is expert systems fail because rules are dumb. Not really, they failed on the knowledge acquisition bottleneck and brittleness. It was hard to get all the rules written down, including the edge cases. And if a rule was not covered, it would fail loudly. And updating those rules also was a challenge, because they grew into large numbers of 600 plus 1000 plus if then rules. Knowledge graphs are legacy tech? No, everything that we are doing in 2026 has a knowledge graph associated with that. If you are trying to ground, yeah, the data coming out, yeah, so it's new. Here are some interview questions that we should always be prepared for. Hey, why is search fundamental to AI? Because reasoning is largely exploring a space and knowing when you are winning. So it's like you're searching for some answers. The catch is exponential blow up. So you don't go and visit all the branches in the graph. It's about learning to prune certain parts of the tree, so that you only visit certain nodes and certain branches. What is a heuristic and how does A star use it? It's good to guess way of guessing answers, and A star ranks by f of n is equal to g of n plus h of n, where we are saying that, hey, what have I learned so far and how can I optimize the next step? That's what it is trying to do. And it is used to find the right answer in systems. How is an LLM agent like classical planning? So imagine the strips that we were talking about. It's like a strips with a neural planner. Uh, Tools are actions, context is the state, and failures are old planning failures. So LLM agent is more like it's using a planner. Certain tools are available for it to act on. When the results come back, it updates the context or the state, and it keeps doing that until it gets to the goal or success criteria, or it reaches a particular state where it can't loop anymore. And what is neurosymbolic AI? We looked at it. Neural language AI is for language and intuition, symbolic for planning and verifiable facts. Often they are used together because together they become more defensible than either alone. And that was the vocabulary that we learned today. We looked at search, how it is used; planning, how are we using it; the knowledge graph that we looked at from an angle of knowledge representation; and finally the bridge, how neural and symbolic AI came together. And in 2026 every agent is built on that framework. In conclusion, we are saying, hey, the search never left, it just changed clothes. It came back in a new format. Yeah, the intelligence is largely disciplined search. That's what we are saying, because the data is everything that's already encoded either in a model or in a knowledge graph. We need to do the right search. Every agent is secretly a 1971 planner. Yeah, that's true. The strips lesson, that's what we learned about. The knowledge is in the world, the hard part was getting it into the machine. uh, that meant that, hey, we were very wrong in doing hand held or hand coded features creation, rules creation, and so on. That was never gonna scale. We learned that through mycin and xcon, are the symbolic AI part of the world. And with that certain limitation, when it combines with neural AI, the neural symbolic era of the world is seeing amazing innovation there, with new agents, agentic frameworks and everything. And that's possible because of a combination of neural AI and symbolic AI. Yeah, intuition on one hand, grounding on truth on one hand, combined together, uh, uh, a jackpot. And that was track B part 2, where we learned about searching, planning, and knowledge representation.